Hello and welcome. We live in a world that is just overflowing with data, absolutely drowning in it sometimes. But the big question is, how do we find the real story inside all of that noise? Well, in this explainer, we are going to look at the powerful statistical tools that researchers use to turn all those numbers into real knowledge to find the truth.
And really, it all comes down to this one question. Think about it. When we see two things happening at the same time, is one actually causing the other, or is it just random chance, a coincidence? The tools we are about to discuss, they are all designed to help us answer that very question with a lot of confidence. So here is our plan for today. First, we'll start with the foundation, how to design a really clean experiment. Then we will look at a very common trap called confounding. After that, we are going to explore how we can predict things using regression models. And finally, we'll see the digital tools that make all of this possible. Okay, let's get right into it. Before we can analyze anything at all, we need good, clean data. You can think of it like this. This first step is all about removing the noise. All those random things that can hide the true effect we are actually trying to find. So one of the most important ways to do this is a technique called blocking. Let's imagine you're testing a new medicine. Now, you already know that a person's age might change how they react, isn't it? So instead of just testing on a random jumble of people, you get smart. You create blocks, one for younger people, one for middle-aged people, and one for older people. Then you test the medicine inside each of those groups separately. And this image, it shows the difference so clearly. On the left side, without any blocking, everything is just a chaotic mix. But look at the right side. That is the organized approach. First, you see we create these neat groups, block 1, block 2, and then you run your experiment inside each of those similar groups. Much better. And what this all does, the whole point of it, is that blocking lets you compare like with like. You're comparing the medicine's effect on young people against other young people, not against older people. You are making sure it's a true apples-to-apples comparison. It sounds simple, but it is so important. Now, even if you design a perfect experiment, data can sometimes play tricks on you. And this brings us to our next big idea, confounding. This is all about a hidden variable, something you might not even see, that can totally fool you. So what is a confounding variable? It's like a ghost in the machine. It's a third factor, something you might not even be measuring, that is secretly influencing both the thing you're studying and the final outcome. It creates a connection that looks real, but is actually false. It's distorted. So this diagram here might look a little technical, but the idea is actually quite simple. You have this confounding variable at the top. And look, it's affecting both the variable on the left and the variable on the right. This makes it look like they are directly connected when they might not be at all. Let's use a real-world example to make this crystal clear. Okay, here is a classic and slightly funny example. The data shows very clearly that on days when ice cream sales go up, so do the number of shark attacks. So what does this mean? Does eating a cone of ice cream somehow make you more attractive to sharks? Of course not. The hidden culprit, the confounding variable, is the temperature. It makes perfect sense when you think about it. When it gets hot, what happens? More people buy ice cream, and more people go swimming in the ocean. The hot weather is causing both things to increase. The ice cream has nothing to do with the shark attacks. And this is why spotting these hidden variables is absolutely critical. So once we have our clean experiment and we are on the lookout for these hidden variables, we can finally move to the analysis. And this is where we use amazing tools like regression models to find the real story that's hiding in the data.
Now, the source material gives us a nice formal definition. But really, regression is all about understanding relationships. It lets us build a mathematical model to see how one or more things, we call them the independent variables, can predict an outcome, the dependent variable. A common example is predicting a house's price based on its size and location.
And regression is not just one tool, it's a whole toolkit. You have linear regression for simple, straight-line relationships, like the more you study, the higher your grades. Then you have logistic regression for yes or no questions, like predicting if a customer will buy something. And there are even more complex types for really messy data. The key is to choose the right tool for the job. So when we build one of these models, how do we know if we found something real or if it's just random noise? That's where something called hypothesis testing comes in. It basically forces us to choose between two stories. The null hypothesis, on the left, it says, nope, we found nothing. Any effect we see is just chance. But the alternative hypothesis, on the right, that's the exciting one. It says, yes, we found something real and significant. This is not just a coincidence. So we've covered some really powerful ideas: blocking, confounding, regression. But how do people actually do this work? Let's move to our final section and have a look at the digital toolbox that makes it all happen. As you can imagine, these complex calculations are not done by hand with a pen and paper. No, they're done using very specialized software. The source material points out some of the most common ones, from something we all know, like Excel, to very powerful dedicated tools like SPSS, Manytab, and even the programming language R. Let's just focus on Excel for a moment, because everyone knows it. We might think of it for making simple lists or a budget, but honestly, it is an incredibly powerful platform for doing serious statistical work. It can handle everything from the very beginning, just entering your data, all the way to doing complex calculations and creating forecasts for the future. At the end of the day, these methods and these software tools, they are the very foundation of modern discovery. They're being used every single day to do amazing things, from developing new life-saving medicines in clinical trials to improving how factories work and understanding complex business trends around the world. So we have gone on a journey, from asking a good question to designing a clean experiment and then using the right tools to find a reliable answer.